In the vast cosmic theatre where gravity dances with space-time itself, there exists a phenomenon so profound and enigmatic that it challenges our very understanding of reality. Black holes represent the ultimate conclusion of gravitational collapse, regions where matter has been compressed to such extraordinary densities that the fabric of space and time becomes so warped that nothing, not even light traveling at its cosmic speed limit, can escape once it crosses a critical boundary. These cosmic enigmas come in various forms and sizes, each with its own fascinating story of formation, characteristics, and the role it plays in shaping the universe around it. And in this video, we will explore every type of black hole. So, watch this video till the end and subscribe to the channel. Let's begin. When we contemplate the smallest members of this mysterious family, we encounter what astronomers classify as stellar mass black holes, objects typically ranging from about 3 to several dozen times the mass of our Sun. These cosmic predators are born from the violent deaths of massive stars, celestial bodies that have exhausted their nuclear fuel and can no longer support themselves against the inexorable pull of their own gravity. The journey toward becoming a stellar mass black hole begins billions of years earlier, when a star much more massive than our Sun forms from collapsing clouds of gas and dust. Throughout its lifetime, this stellar giant fuses hydrogen into helium in its core, then progresses through successive stages of nuclear fusion, creating heavier and heavier elements. Iron represents the end of this productive fusion process, because fusing iron consumes energy rather than releasing it. And when the core becomes predominantly iron, the star faces its ultimate crisis. The core collapse happens with breathtaking speed, taking less than a second for the inner regions of the star to fall inward at velocities approaching a quarter of the speed of light. The infalling material rebounds off the incredibly dense proto-neutron star forming at the center, generating a catastrophic explosion we observe as a supernova, one of the most energetic events in the cosmos. However, if the original star was sufficiently massive, typically more than 20 to 25 solar masses, depending on various factors like rotation and composition, even the immense pressure of neutron degeneracy cannot halt the collapse. The core continues to compress beyond the neutron star stage, shrinking past the point of no return, and a stellar mass black hole is born, cloaked in darkness at the heart of an expanding cloud of stellar debris. These stellar remnants possess characteristics that seem to defy common sense, yet emerge naturally from Einstein's general theory of relativity. At the heart of every black hole lies what physicists call a singularity, a point where matter is compressed to infinite density, and the known laws of physics break down completely. Surrounding this singularity exists the event horizon, an invisible spherical boundary that marks the point beyond which escape becomes impossible. The radius of this boundary, known as the Schwarzschild radius, depends directly on the black hole's mass, with more massive black holes possessing proportionally larger event horizons. For a stellar mass black hole of 10 solar masses, this boundary would sit at a radius of roughly 30 kilometers, creating a sphere from which no information can ever return to the outside universe. The extreme warping of space-time near these objects produces effects that would seem fantastical if they weren't rigorously predicted by mathematical physics. An observer watching an object fall toward a black hole would witness that object's descent appear to slow dramatically as it approaches the event horizon, with light from the falling object becoming increasingly redshifted, stretched toward longer wavelengths by the immense gravitational field. The falling object would appear to freeze at the horizon, gradually fading from view as its light is redshifted beyond detection. Even though from the perspective of the falling observer, they would cross the horizon in finite time without noticing anything particularly special about that exact moment. This divergence between perspectives represents one of the most mind-bending aspects of black hole physics. revealing how gravity doesn't just bend space, but fundamentally alters the flow of time itself. Stellar mass. Black holes rarely exist in isolation, and when they find themselves in binary systems with ordinary stars, they can create some of the most spectacular phenomena in observational astronomy. As the black hole's immense gravity pulls material away from its companion star, this stolen gas doesn't fall directly into the black hole, but instead forms a swirling accretion disk, a flattened structure where friction between particles converts gravitational potential energy into intense heat. The inner regions of these accretion disks can reach temperatures of millions of degrees, causing them to radiate powerfully in X-rays. These X-ray binary systems served as the first compelling evidence for stellar mass black holes, with Cygnus X1 discovered in 1964, standing as one of the most famous examples. Observations of the visible companion star revealed it was orbiting an invisible object far too massive to be a neutron star, with careful measurements indicating a mass of approximately 15 solar masses, well above the theoretical maximum for any object supported by degeneracy pressure. The material spiraling into these black holes doesn't simply disappear quietly, but can generate some of the most energetic phenomena we observe in the universe. As matter in the accretion disk spirals inward, it reaches velocities approaching significant fractions of light speed, and the intense magnetic fields threading through the disk can channel some of this material into narrow jets perpendicular to the disk's plane. These relativistic jets, streams of particles moving at speeds exceeding 99% of light speed, extend for enormous distances and produce radiation across the entire electromagnetic spectrum. The mechanisms powering these jets involve a complex interplay between the magnetic fields, the rotation of the black hole itself through a process involving what physicists call the ergosphere, and the dynamics of the accretion flow, representing one of the most active areas of research in high-energy astrophysics. Moving up the mass scale, we encounter intermediate mass black holes, objects residing in a curious gap between their stellar cousins and the supermassive monsters lurking in galactic centers. With masses ranging from roughly 100 to 100,000 solar masses, these objects have proven remarkably elusive, with only a handful of candidate detections despite decades of searching. The difficulty in finding intermediate mass black holes stems partly from the fact that they're too massive to form through the death of individual stars, yet not massive enough to sit at the centers of galaxies, where we routinely find their supermassive relatives. Theoretical models suggest several possible formation pathways for these mysterious objects, each involving somewhat exotic scenarios that may have been more common in the early universe or in particularly dense stellar environments. One proposed formation mechanism involves the direct collapse of massive stars in the early universe, shortly after the first generation of stars began forming. These primordial stars, composed almost entirely of hydrogen and helium, without the heavier elements produced by later stellar generations, could have grown to truly enormous masses, perhaps several hundred solar masses, significantly larger than stars forming in the present-day universe. When these giants exhausted their fuel, they might have collapsed directly to form black holes without the intermediate supernova explosion, seeding the early universe with intermediate mass black holes that could serve as building blocks for the supermassive black holes we observe today. Alternative scenarios involve the collision and merger of stellar mass black holes in extremely dense stellar environments, like the cores of globular clusters, ancient collections of stars that orbit galaxies in spherical swarms. In these crowded environments, stellar mass black holes might gradually coalesce through repeated mergers over billions of years, progressively building up intermediate mass black holes through this cosmic accumulation process. Evidence for intermediate mass black holes remains tantalizingly inconclusive, but has strengthened in recent years through multiple independent lines of investigation. Some of the most compelling hints come from observations of ultraluminous X-ray sources, mysterious objects that shine far more brightly in X-rays than typical stellar mass black hole systems, yet appear too luminous to be explained by accretion onto normal stellar remnants. The extreme luminosity of these sources suggests they might harbor intermediate mass black holes, whose larger event horizons allow them to accrete matter at higher rates than their smaller cousins. Additional evidence has emerged from careful studies of the velocities of stars in the centers of globular clusters, where the measured stellar motions seem to require the presence of a central massive object. Though alternative explanations involving clusters of stellar remnants remain viable in many cases. The detection of gravitational waves by facilities like LIGO and Virgo has opened an entirely new window into the black hole population, allowing scientists to detect mergers of these invisible objects through the ripples they create in spacetime itself. In 2019, astronomers announced a particularly intriguing detection involving a black hole merger that produced a final object of roughly 142 solar masses, with the two progenitor black holes weighing approximately 85 and 66 solar masses, respectively. This detection proved significant because the masses of the merging black holes fell into what theorists call the pair instability gap, a mass range where stellar evolution theory suggests black holes shouldn't exist because massive stars in this range should completely destroy themselves in pair instability, supernovae, rather than leaving behind black hole remnants. The observation raised fascinating questions about either the formation of these objects or our understanding of late-stage stellar evolution, while the final merged object comfortably qualified as an intermediate mass black hole, providing perhaps the most unambiguous detection of this elusive class. At the opposite end of the mass spectrum, from stellar remnants tower, the supermassive black holes, behemoths containing millions to billions of solar masses that occupy the central regions of most large galaxies, including our own Milky Way. These cosmic giants play crucial roles in galactic evolution, influencing star formation, gas dynamics, and the overall structure of their host galaxies through processes collectively termed active galactic nucleus feedback. The black hole at the center of our galaxy, known as Sagittarius A, or Esger A for short, contains approximately 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun. For decades, astronomers tracked individual stars orbiting this invisible giant, watching them whip around at velocities exceeding 10,000 kilometers per second, their elliptical paths providing ironclad evidence for an enormous mass concentration in an incredibly small volume, leaving a black hole as the only plausible explanation. The formation of supermassive black holes represents one of the deepest mysteries in astrophysics, particularly given that we observe fully formed giants containing billions of solar masses when the universe was less than 1 billion years old, barely 7% of its current age. Growing a black hole from stellar mass seeds to billions of solar masses in such a short cosmic timespan requires sustained accretion at extraordinarily high rates, likely near or even exceeding the Eddington limit, the theoretical maximum rate at which an object can accrete matter before the radiation pressure from the accretion process itself blows away incoming material. Several competing theories attempt to explain how supermassive black holes achieved their enormous masses so quickly in the early universe. Some models invoke the collapse of massive primordial gas clouds directly into intermediate mass black hole seeds that could then grow more rapidly than stellar mass seeds. Others propose that dense stellar clusters in the early universe might have undergone runaway collisions, with stars merging together to build a supermassive star that would then collapse into a large seed black hole. A third possibility involves sustained super-Eddington accretion onto stellar mass seeds under the special conditions present in the early universe, though this requires somewhat fine-tuned circumstances to overcome the natural tendency for radiation pressure to limit accretion rates. When supermassive black holes actively accrete large amounts of material, they manifest as quasars, among the most luminous objects in the universe, with the brightest examples outshining their entire host galaxies by factors of 100 or more. The term quasar derives from quasi-stellar radio source, reflecting the fact that these objects appeared point-like in optical images, similar to stars, yet possessed peculiar properties that quickly revealed their extragalactic nature. The immense luminosity of quasars arises from the conversion of gravitational potential energy into radiation, as matter spirals into the supermassive black hole, with the accretion process achieving efficiencies that would make fusion reactors jealous. While nuclear fusion converts roughly 1% of mass into energy, black hole accretion can convert 10% or more of infalling mass into radiation, making it the most efficient energy generation process known in nature, aside from matter-antimatter annihilation. The discovery that nearly all large galaxies harbor supermassive black holes at their centers, even those showing no signs of active accretion in the present day, revolutionized our understanding of galactic evolution. Observations revealed tight correlations between black hole mass and various properties of their host galaxy's central bulge, including the bulge's total stellar mass and the velocity dispersion of stars in the bulge. These correlations suggested that black holes and galaxies don't evolve independently, but instead co-evolve through intimately connected processes. The energy released during periods of active accretion can heat or expel gas from the galaxy, regulating star formation and preventing the galaxy from growing too large, while the galaxy's merger history determines when fresh supplies of gas fall toward the central black hole, triggering new episodes of accretion. This feedback loop between black holes and their host galaxies helps explain why galaxies follow fairly tight relationships between their properties, rather than exhibiting a wider range of possible configurations. The immediate environment around actively accreting supermassive black holes displays a rich phenomenology spanning multiple spatial scales. Closest to the event horizon lies the accretion disk itself, where material orbits at relativistic velocities in a structure that may extend from just a few Schwarzschild radii outward to thousands or even millions of radii. The inner disk reaches temperatures of hundreds of thousands or even millions of degrees, radiating primarily in the ultraviolet and X-ray portions of the spectrum, while cooler outer regions emit in optical and infrared light. Strong magnetic fields permeate the disk, contributing to the transport of angular momentum that allows material to gradually spiral inward, while also powering phenomena like relativistic jets and disk winds that can carry mass and energy away from the system. Perpendicular to the disk plane, relativistic jets can extend for millions of light years, creating enormous radio lobes when they slam into the intergalactic medium and acting as one of the primary mechanisms through which black holes inject energy into their surroundings. Surrounding the accretion disk, observations reveal regions of rapidly moving gas clouds arranged in complex geometries. Broad emission line regions contain gas clouds moving at velocities of thousands of kilometers per second, at distances of light days to light months from the central black hole, while narrow emission line regions contain slower moving material at much greater distances of thousands of light years. Many active galactic nuclei also show evidence for a dusty torus, a roughly donut-shaped structure of dust and gas surrounding the inner regions, with the observer's viewing angle relative to this torus helping to determine whether we classify the object as a particular subtype of active galaxy. Objects viewed face-on through the hole in the donut might appear as Type 1 quasars, showing both broad and narrow emission lines, while those viewed edge-on through the dusty torus might appear as Type 2 objects, where the torus obscures our direct view of the broadline region and inner accretion disk. In 2019, the world marveled at humanity's first direct image of a black hole's shadow, captured by the Event Horizon Telescope collaboration through a coordinated observation involving radio telescopes scattered across Earth, effectively creating a planet-sized instrument. The target, the supermassive black hole at the center of the galaxy. Messier 87 revealed itself as a dark circular shadow surrounded by a bright ring of emission from the accretion disk. The asymmetry in the brightness around the ring reflected relativistic beaming effects, where material moving toward us appears brighter due to Doppler boosting, while material moving away appears dimmer. This historic image confirmed decades of theoretical predictions about the appearance of black holes and demonstrated the reality of event horizons, those boundaries beyond which no information can escape. Just 3 years later, the same collaboration released an image of Sagittarius A, the black hole at our own galactic center, revealing a similar shadowed structure, albeit more difficult to image due to rapid variability in the accretion flow on timescales of minutes. Beyond supermassive black holes lies an even more exotic category, the ultramassive black holes, objects exceeding 10 billion solar masses that occupy the centers of the most massive galaxies in the universe. These titans push the boundaries of how large black holes can grow, with the current record holder, the black hole in the galaxy, Holm 15A, estimated to contain roughly 40 billion solar masses based on measurements of stellar velocities in the galaxy's core. The extreme masses of these objects raise questions about the limits to black hole growth and whether physical processes exist that naturally cap how large these objects can become. Some theoretical work suggests that the most massive black holes might actually hinder their own growth by heating surrounding gas so effectively that further accretion becomes increasingly difficult, potentially establishing a natural upper limit to black hole masses around 50 billion solar masses, though this remains an active area of investigation. The formation of ultramassive black holes likely requires special circumstances beyond the growth mechanisms sufficient for regular supermassive black holes. Galaxy mergers provide one promising pathway, as when two galaxies collide and merge, their central black holes eventually sink toward the center of the merged system through dynamical friction, the gravitational drag exerted by surrounding stars. After forming a binary pair, the black holes gradually spiral together, losing orbital energy through gravitational wave emission. Once they approach close enough, ultimately merging into a single, more massive black hole. Major mergers between galaxies containing billion solar mass black holes could produce ultramassive black holes, particularly if the merged galaxy subsequently experiences additional mergers in a rich cluster environment. The largest black holes we observe today likely experienced multiple major merger events throughout cosmic history, progressively building their masses through this hierarchical growth process. A particularly exotic and entirely theoretical class of black holes consists of primordial black holes, objects that might have formed in the very early universe, fractions of a second after the Big Bang, through mechanisms completely unrelated to stellar evolution. During the first moments of cosmic history, tiny quantum fluctuations in the density of the expanding universe might have produced regions where matter was compressed densely enough to undergo gravitational collapse directly, forming black holes with masses potentially ranging from a tiny fraction of a gram up to thousands of solar masses, depending on the exact timing and conditions of formation. These primordial black holes would differ fundamentally from their stellar origin cousins in several ways. They could possess masses far below the minimum required for stellar collapse, including miniature black holes lighter than Earth, and their abundance and mass distribution would carry information about the physics of the extremely early universe, potentially even offering a window into conditions during cosmic inflation. The potential existence of primordial black holes has captivated researchers for decades because they might solve several outstanding puzzles in cosmology and astrophysics. One particularly intriguing possibility suggests that primordial black holes could comprise some or all of the dark matter, the mysterious substance that makes up approximately 27% of the universe's mass-energy budget, yet doesn't interact with light or normal matter except through gravity. If primordial black holes exist in sufficient numbers and with the right mass distribution, they could provide the gravitational scaffolding that holds galaxies together and creates the large-scale structure of the universe, all without requiring any exotic new particles beyond the standard model of particle physics. However, numerous observational constraints have ruled out primordial black holes as the dominant component of dark matter for most potential mass ranges, with particularly strong limits coming from micro-lensing surveys that would detect primordial black holes through their gravitational lensing effects if they existed in large numbers. The search for primordial black holes continues through multiple observational channels, with researchers particularly interested in the mass ranges not yet definitively excluded. Gravitational wave detections offer one promising avenue, as mergers between primordial black holes would produce signals potentially distinguishable from stellar origin black hole mergers through statistical properties of the population. The existence of black holes in the pair instability gap mentioned earlier has even raised speculation about primordial origins for some objects detected by LIGO and Virgo, though other explanations involving unusual stellar evolution or hierarchical mergers remain viable. Future gravitational wave detectors with improved sensitivity might detect a population of mergers involving black holes lighter than stellar remnants, which would strongly suggest a primordial origin since no known astrophysical process produces black holes in that mass range. At the opposite extreme, from massive primordial black holes, Stephen Hawking's theoretical work in the 1970s revealed that quantum effects near black hole event horizons lead to remarkable consequences for the smallest possible black holes. Hawking showed that black holes aren't perfectly black, but actually emit thermal radiation through a quantum mechanical process involving particle-antiparticle pairs forming near the event horizon, with one particle occasionally escaping while its partner falls into the black hole. This Hawking radiation means that black holes gradually lose mass over time, evaporating increasingly rapidly as they shrink. For stellar mass and larger black holes, the Hawking radiation is utterly negligible, with the temperature of a solar mass black hole amounting to only 60 nanokelvins, far colder than the cosmic microwave background radiation permeating space. However, for sufficiently small black holes, Hawking radiation becomes significant and eventually dominant. The evaporation time for a black hole scales with the cube of its mass, meaning smaller black holes evaporate exponentially faster than larger ones. A hypothetical miniature black hole with the mass of a large asteroid, say 1 trillion kilograms, would evaporate completely in about 80 billion years, longer than the current age of the universe. Reduce the mass to 100 million kilograms, roughly the mass of a supertanker, and the evaporation time drops to about 2,500 years. A black hole with the mass of a mountain, around 10 billion kilograms, would last merely a few minutes before disappearing in a burst of radiation. If any miniature primordial black holes formed in the early universe with masses much below about 10 to the power of 11 kilograms, they would have already evaporated by now, potentially contributing to the background radiation we observe today, though this contribution would be extremely difficult to distinguish from other radiation sources. The final moments of black hole evaporation remain shrouded in theoretical uncertainty because they require a complete theory of quantum gravity, which continues to elude physicists despite decades of effort. As a black hole shrinks to Planck-scale dimensions, roughly 10 to the minus 35 meters, our current understanding of physics breaks down completely, and neither general relativity nor quantum field theory can reliably describe what happens. The fate of information that falls into black holes represents one of the deepest puzzles in theoretical physics, with Hawking's original calculations suggesting that information is destroyed, violating a fundamental principle of quantum mechanics. This black hole information paradox has sparked intense debate and inspired numerous proposed solutions, from subtle quantum corrections that encode information in the Hawking radiation to more radical ideas involving black holes as portals to other universes or modifications to quantum mechanics itself. Rotating black holes possess properties markedly different from their non-rotating cousins, described mathematically by the Kerr solution to Einstein's equations rather than the simpler Schwarzschild solution applicable to static black holes. Rotation adds complexity and richness to black hole spacetime geometry, creating a region called the ergosphere surrounding the event horizon, where the dragging of spacetime by the black hole's spin becomes so extreme that nothing can remain stationary relative to distant observers. Everything must rotate along with the spinning black hole. The ergosphere's outer boundary, the surface where this dragging effect begins, touches the event horizon at the black hole's poles but extends farther out at the equator, with the size depending on the rotation rate. For maximally rotating black holes, the ergosphere extends to twice the Schwarzschild radius at the equator. The existence of the ergosphere enables a remarkable process called the Penrose mechanism, proposed by Roger Penrose in 1969, through which energy can be extracted from a rotating black hole. If an object enters the ergosphere and splits into two pieces, with one piece falling into the black hole while the other escapes, the escaping piece can emerge with more energy than the original object possessed, with the extra energy coming from the rotational energy of the black hole itself. While this might sound like getting something for nothing, the infalling piece carries negative energy as measured by distant observers, slowing the black hole's rotation and reducing its mass energy by exactly the amount gained by the escaping piece. This energy extraction process respects all conservation laws while demonstrating that black holes can serve as energy sources, not just cosmic sinks. In astrophysical contexts, the Penrose mechanism likely operates through the interaction between magnetic fields and the rotating spacetime geometry, a process called the Blandford-Znaeck mechanism, after the physicists who first described it in detail. Magnetic field lines threading through the black hole's horizon can tap into its rotational energy, channeling power into the relativistic jets observed emerging from many active galactic nuclei and stellar mass black hole systems. Observations of jet power in various systems suggest that this spin-powered mechanism plays a crucial role in energizing the jets, with the most powerful jets appearing to come from rapidly spinning black holes. The correlation between jet power and black hole spin provides indirect evidence that many black holes in nature rotate at substantial fractions of the maximum possible rate. Charged black holes represent another theoretically interesting variant, described by the Reissner-Nordström solution for non-rotating charged black holes, or the Kerr-Newman solution for rotating charged black holes. A charged black hole possesses two horizons rather than one, with the outer event horizon similar to the horizon of an uncharged black hole, while an inner Cauchy horizon lies deeper within. The structure of spacetime inside a charged black hole differs dramatically from the simpler Schwarzschild case, with the singularity taking the form of a ring rather than a point for rotating charged black holes, and in principle allowing for exotic possibilities like traversable pathways through the singularity or transitions to other universe regions. Though these features likely remain purely mathematical artifacts rather than physically realizable structures. Despite their theoretical interest, charged black holes almost certainly don't exist in nature with significant net charge. Any substantial electric charge on a black hole would quickly attract opposite charges from the surrounding environment, rapidly neutralizing the black hole through accretion of charged particles. The maximum plausible charge for an astrophysical black hole amounts to a tiny fraction of the charge required to significantly affect the spacetime geometry. meaning that for practical purposes, real black holes are effectively described by the Kerr solution for rotating uncharged black holes. Nevertheless, the mathematical study of charged black holes has proven valuable for understanding the general properties of black hole solutions and for investigating Gedanken experiments in black hole physics. Black hole mergers represent one of the most violent events in the universe, releasing more power during the final moments of coalescence than all the stars in the observable universe combined, though all that power emerges as gravitational waves rather than electromagnetic radiation. When two black holes orbit each other, they gradually spiral together as they lose orbital energy to gravitational wave emission, following a death spiral that can last billions of years for widely separated black holes, but accelerates dramatically as they approach. In the final seconds before merger, the black holes orbit each other hundreds of times per second, whipping spacetime into a frenzy and emitting gravitational waves of increasing amplitude and frequency. The actual merger, when the two event horizons touch and merge into a single horizon, happens remarkably quickly, taking only a few orbits, and the resulting merged black hole rings down like a struck bell, emitting gravitational waves at characteristic frequencies as it settles into its final Kerr configuration. The gravitational wave signal from a black hole merger carries a wealth of information encoded in its waveform, allowing scientists to extract the masses and spins of the merging black holes, their distance from Earth, and properties of the final merged object. The loudness of the signal depends on the total mass of the system and the distance to the merger, with more massive systems and closer mergers producing stronger signals. The frequency evolution reveals the component masses, since heavier black holes orbit more slowly for a given separation, while lighter black holes orbit more rapidly. The maximum frequency reached before merger depends on the total mass, with stellar mass black hole mergers producing gravitational waves with frequencies of tens to thousands of hertz, perfect for detection by ground-based interferometers like LIGO and Virgo, while supermassive black hole mergers produce millihertz gravitational waves requiring space-based detectors like the planned LISA mission. Since the first gravitational wave detection in 2015, the LIGO-Virgo-Kagra collaboration has detected dozens of black hole mergers, revolutionizing our understanding of the black hole population and revealing surprises about the properties of binary black holes in the universe. The detected systems show a wide range of mass combinations, from roughly equal mass binaries to asymmetric systems where one black hole significantly outweighs the other. The distribution of black hole masses revealed by gravitational wave detections differs somewhat from expectations based on electromagnetic observations of X-ray binaries, with gravitational wave detections finding black holes that appear more massive on average than those seen in X-ray systems, suggesting that the population of black holes formed throughout cosmic history is more diverse than previously recognized. The spins of merging black holes provide crucial information about their formation history, distinguishing between different formation channels. Black holes that formed in binary star systems that remained bound throughout their evolution might show aligned spins, with both black holes spinning in the same direction as the orbital motion, reflecting the original angular momentum of the stellar binary. In contrast, black holes that formed separately and later paired up through dynamical interactions in dense stellar environments would show randomly oriented spins with no preferred alignment relative to the orbital plane. The gravitational wave data suggests that both formation channels contribute to the observed merger population, with some systems showing aligned spins consistent with field binary evolution, and others showing misaligned spins pointing toward dynamical formation. Tidal disruption events provide a spectacular demonstration of black hole physics when a star wanders too close to a black hole and gets torn apart by tidal forces. The difference in gravitational pull between the star's near and far sides exceeding the star's self-gravity. The critical distance where tidal disruption occurs depends on both the black hole mass and the star's radius and density, with the tidal disruption radius lying outside the event horizon for black holes below about 100 million solar masses, but falling inside the event horizon for more massive black holes. This means that supermassive black holes in the mass range of millions to tens of millions of solar masses are optimal for producing observable tidal disruption events, while ultramassive black holes simply swallow stars whole without creating much of a spectacle. When a star gets tidally disrupted, roughly half of the stellar material remains bound to the black hole and quickly settles into an accretion disk, while the other half is ejected at high velocities. The sudden accretion of stellar material onto a previously quiescent black hole produces a bright flare of electromagnetic radiation that can outshine the entire host galaxy for weeks or months, with the light curve showing a characteristic decline over time as the accretion rate gradually decreases. Astronomers have discovered hundreds of candidate tidal disruption events through optical, ultraviolet, and X-ray surveys, with the rate of detections accelerating as new wide-field time-domain surveys come online. These events provide unique laboratories for studying black holes that otherwise remain dormant, allowing measurements of black hole masses and spins, and probing the physics of accretion flows during a well-defined beginning rather than during a steady-state phase. The information paradox mentioned earlier in the context of miniature evaporating black holes actually applies to black holes of all sizes and represents one of the deepest conceptual problems in fundamental physics. The paradox arises from the apparent conflict between quantum mechanics, which insists that information cannot be destroyed, and Hawking's calculation showing that black hole evaporation produces perfectly thermal radiation carrying no information about what fell into the black hole. If black holes destroy information, quantum mechanics as we understand it is wrong. If information somehow escapes in the Hawking radiation, Hawking's calculation based on quantum field theory in curved spacetime must be missing something crucial. Neither option is particularly palatable, suggesting that the paradox points toward new physics we haven't yet uncovered. Recent theoretical work has made significant progress toward resolving the information paradox, with many physicists now believing that information does eventually escape from black holes through subtle quantum mechanical correlations in the Hawking radiation, though the details remain hotly debated. The key insight involves recognizing that Hawking's original calculation, while correct in many respects, didn't properly account for quantum gravitational effects that become important when considering the entire evaporation process. When these effects are included, using modern tools from string theory and quantum information theory, the radiation shows deviations from perfect thermality precisely when and how needed to preserve information. The black hole's interior and exterior turn out to be quantum mechanically entangled in ways that allow information to be encoded in subtle correlations between different parts of the Hawking radiation, though recovering that information would require impossibly precise measurements of the radiation over the entire evaporation process. Gravitational lensing by black holes provides another arena where their extreme gravity reveals itself through observable effects. When a black hole passes between Earth and a more distant light source, its gravity bends the light rays from the background source, typically creating multiple distorted images and amplifying the total brightness we observe. For stellar mass black holes, microlensing events occur when a black hole passes nearly in front of a background star, causing the star's apparent brightness to temporarily increase following a characteristic symmetric light curve, lasting weeks to months depending on the black hole's mass and velocity. Large surveys monitoring millions of stars in nearby galaxies or in our own galactic bulge have detected thousands of microlensing events, with some fraction likely caused by black holes, though definitively identifying black hole events remains challenging since stellar remnants of all types can produce similar lensing signatures. For supermassive black holes in galactic centers, strong gravitational lensing can create spectacular Einstein rings or multiple images of background galaxies when the geometric alignment is favorable. In a few exceptional cases, the lensing black hole and background source align so precisely that we observe an almost perfect ring of light around the lensing galaxy, the background source's light forming a circular image around the lensing galaxy's position. These Einstein rings provide beautiful demonstrations of general relativity's predictions and allow precise measurements of the lensing black hole's mass by analyzing the ring's size and shape. The imaging of black hole shadows by the Event Horizon Telescope represents an extreme case of gravitational lensing, where we observe light from the accretion disk bent by the black hole's gravity into a circular pattern around the shadow. The study of black holes through electromagnetic observations, gravitational wave detections, and theoretical investigations has profoundly expanded our understanding of these objects over the past decades. Yet fundamental questions remain open and active areas of research. The mechanisms that seed supermassive black holes in the early universe continue to puzzle astronomers, as do the detailed processes through which black holes co-evolve with their host galaxies. The spins of black holes, which encode information about their formation and growth histories, remain difficult to measure reliably in most systems, though improving observational techniques offer hope for better constraints in coming years. The nature of the singularities at black hole centers remains mysterious, likely requiring a complete theory of quantum gravity to fully understand, and the information paradox, while showing promising signs of resolution, has not reached complete consensus among theoretical physicists. Future observations promise to revolutionize our understanding of black holes across the mass spectrum. The next generation of gravitational wave detectors, including space-based missions like LISA and improved ground-based facilities like Cosmic Explorer and Einstein Telescope, will detect black hole mergers across cosmic history and access the supermassive black hole merger population currently beyond our reach. Continued expansion of the Event Horizon Telescope Array and possible space-based black hole imaging missions could provide movies of matter orbiting black holes rather than static images, revealing the dynamics of accretion flows and jet launching in unprecedented detail. Upcoming electromagnetic surveys in multiple wavelengths will discover new classes of black hole systems and rare events, building more complete census of the black hole population and testing theoretical models with better statistics. The interplay between black holes and their environments extends to cosmological scales, with black holes potentially affecting the evolution of the universe as a whole through their contributions to cosmic energy budgets and structure formation. The energy released by accreting black holes throughout cosmic history, while tiny compared to the total energy content of the universe, plays an outsized role in regulating the formation of large galaxies and preventing too much cosmic gas from collapsing into stars. Without black hole feedback, the universe would look markedly different, with galaxies growing too large and converting too much of their gas into stars too quickly, yielding a cosmos quite unlike what we observe. This feedback operates through multiple channels, including radiation pressure from accretion disks, mechanical work done by jets slamming into surrounding gas, and cosmic rays accelerated in black hole magnetospheres, with the relative importance of these channels depending on the black hole's accretion state and the properties of its environment. The relationship between black holes and dark energy, the mysterious component driving the universe's accelerated expansion, has recently sparked intriguing speculation among theoretical physicists. Some researchers have proposed that black holes might themselves be sources of dark energy, with the vacuum energy inside their event horizons contributing to the cosmological constant that governs cosmic acceleration. According to these models, as the universe ages and more black holes form through stellar evolution and mergers, the total amount of dark energy increases, potentially explaining why dark energy appears to dominate the universe's energy budget only in relatively recent cosmic epochs. While these ideas remain highly speculative and face significant theoretical challenges, they illustrate how black holes might connect to the deepest mysteries in cosmology, bridging the physics of extreme gravitational collapse with the large-scale evolution of space-time itself. Black holes also serve as natural laboratories for testing general relativity in its most extreme regime, where gravitational fields reach strengths impossible to reproduce in terrestrial experiments or anywhere else in the accessible universe. The motion of matter in the intense gravitational fields near black holes, the propagation of light along severely curved space-time trajectories, and the generation of gravitational waves during mergers all provide precision tests of Einstein's century-old theory. So far, general relativity has passed every test with flying colours, with observations agreeing with predictions to remarkable precision. The shadow size observed by the Event Horizon Telescope matched theoretical expectations based on general relativity to within measurement uncertainties. Gravitational wave signals from merging black holes follow the waveforms predicted by general relativity through more than 100 orbits of inspiral and merger. Stars orbiting Sagittarius. Trace out the elliptical paths predicted by general relativity, including subtle effects like the precession of orbital perihelia that provided one of the first confirmations of general relativity in observations of Mercury's orbit around the Sun. Nevertheless, physicists remain keenly interested in searching for deviations from general relativity that might point toward new physics, particularly modifications that might become apparent only in the strongest gravitational fields near black hole horizons. Alternative theories of gravity predict various modifications to black hole properties, potentially changing the relationship between mass and horizon size, altering the structure of space-time near the horizon in detectable ways, or modifying the gravitational wave signals from mergers. Some alternatives to general relativity allow for black hole solutions with surfaces other than event horizons, exotic compact objects that might mimic many black hole properties while avoiding singularities and event horizons entirely. Distinguishing these alternatives from true general relativistic black holes requires exquisitely precise observations, pushing observational techniques to their limits. But the payoff of potentially discovering physics beyond Einstein's theory motivates continued refinement of these tests. The quantum nature of black holes extends beyond Hawking radiation to encompass a rich web of connections between black hole physics, quantum information theory, thermodynamics, and the fundamental structure of space-time itself. Black holes possess thermodynamic properties, including temperature and entropy, with the temperature given by the famous formula derived by Hawking, showing that temperature is inversely proportional to mass. More surprisingly, the entropy of a black hole turns out to be proportional to the surface area of its event horizon rather than its volume, with the proportionality constant involving fundamental constants of nature in a specific combination. This area law for black hole entropy has profound implications, suggesting that the maximum information that can be stored in any region of space is limited by the area of that region's boundary rather than its volume, a principle that has inspired holographic theories of quantum gravity proposing that the physics of space-time might be encoded on lower dimensional boundaries. The holographic principle, which emerged from the study of black hole thermodynamics, proposes that the complete description of any region of space, including everything happening inside it, can be encoded on that region's boundary. This idea finds its most concrete realization in the ADS-CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997, connecting gravitational theories in certain curved spacetimes to quantum field theories living on the boundary of those spacetimes. While the specific spacetimes where this duality is proven don't describe our universe directly, The correspondence has provided crucial insights into quantum gravity and black hole physics, allowing questions about black holes that are intractable in gravitational language to be reformulated as questions in quantum field theory, where powerful mathematical tools apply. Many of the recent insights into black hole information and the resolution of paradoxes have come from studying black holes through this holographic lens. Black holes also feature prominently in various speculative ideas about the nature of reality and the possibility of exotic spacetime structures. Wormholes, hypothetical tunnels connecting distant regions of spacetime or even different universes, are closely related mathematically to black holes, with certain black hole solutions containing wormhole-like structures in their interiors, though these typically don't allow for traversable connections due to the presence of event horizons and singularities. Creating a traversable wormhole would require exotic matter with negative energy density, which quantum field theory allows in principle, but only under very restricted circumstances and in minute quantities, making macroscopic traversable wormholes appear unlikely based on known physics. Nevertheless, wormholes continue to inspire both scientific speculation about possibilities allowed by general relativity and countless science fiction stories, imagining shortcuts through space-time. The possibility that our universe itself might have formed from a black hole in a parent universe represents another exotic idea that some physicists have explored. In these scenarios, the Big Bang that began our universe corresponds to the formation of a black hole as viewed from the parent universe, with the singularity at the black hole's center corresponding to the Big Bang singularity from our perspective. The interior of the black hole becomes a new expanding universe, potentially with different physical constants or laws than the parent universe. While these multiverse scenarios are extraordinarily difficult to test experimentally, since we have no way to observe or interact with universes outside our own, they illustrate how black holes might fit into larger cosmological frameworks and how the physics of black hole singularities might connect to the origin of universes. Returning to more observationally grounded topics, the study of black hole accretion has matured enormously through combinations of improved observations across the electromagnetic spectrum and sophisticated numerical simulations solving the equations governing magnetized fluid dynamics in the extreme environment near black holes. Modern simulations can follow the behavior of accretion flows from large distances where the gas begins falling toward the black hole all the way down to the event horizon, capturing the complex interplay between gravity, gas pressure, magnetic fields, and radiation. These simulations reveal that accretion flows exhibit rich variability on multiple timescales, with turbulence driven by magnetic instabilities stirring the flow and producing the flickering we observe in many black hole systems. The simulations have also illuminated the conditions under which relativistic jets form, showing that strong magnetic fields threading the black hole and the inner accretion disk appear essential for launching and collimating jets. Different accretion states have been identified in stellar mass black hole systems through careful monitoring of their X-ray emission and other properties. In the hard state, the X-ray emission shows a power law spectrum extending to high energies, likely arising from a hot, geometrically thick accretion flow close to the black hole, while a relatively weak jet typically appears in radio observations. The soft state shows X-ray emission dominated by thermal radiation from a cool, geometrically thin accretion disk extending down close to the innermost stable orbit, with jets largely suppressed. Transitions between these states correlate with changes in the accretion rate, with systems generally entering the soft state when accretion rates increase beyond a critical threshold. Some systems show dramatic state transitions on timescales of days or weeks, flipping between jet-dominated and disk-dominated emission patterns, while others remain stubbornly in one state for years. The innermost stable circular orbit plays a special role in black hole accretion physics, representing the closest distance at which matter can maintain a stable circular orbit around the black hole. Inside this radius, there are no stable circular orbits, and matter inexorably plunges into the black hole on a timescale much shorter than the orbital timescale. For non-rotating black holes, the innermost stable circular orbit sits at 3 Schwarzschild radii, while for maximally rotating black holes, it can extend down to just half a Schwarzschild radius for orbits in the same direction as the black hole's spin, or out to 4.5 Schwarzschild radii for orbits in the opposite direction. The location of this innermost stable orbit determines where the accretion disk truncates, affecting the disk's temperature profile and emission spectrum in ways that can be detected observationally, providing one of the methods astronomers use to measure black hole spins. X-ray reflection spectroscopy provides another powerful technique for probing the inner regions of accretion disks and measuring black hole spins. When high-energy X-rays produced in a hot corona above the accretion disk illuminate the disk's surface, some of this radiation gets reflected, producing characteristic spectral features, including a strong iron fluorescence line. The properties of this reflected emission carry information about the geometry and kinematics of the inner disk, with the line profile broadened and skewed by Doppler effects from the disk's orbital motion and gravitational redshifts from the black hole's gravity. Detailed modeling of these spectral distortions reveals where the disk's inner edge sits, which in turn constrains the black hole's spin. Since rapidly spinning black holes allow disks to extend closer to the horizon than slowly spinning ones. Dozens of black hole spins have now been measured using this reflection technique, revealing that black holes span the full range from nearly non-rotating to rapidly spinning, though with some indication that stellar mass black holes in X-ray binaries tend toward higher spins on average. The dynamics of binary black holes before they merge provides insights into their formation and the environments they formed in. When two black holes orbit each other at large separations, their orbital evolution proceeds primarily through gravitational wave emission, gradually shrinking the orbit as orbital energy radiates away. However, in systems that formed through dynamical capture in dense stellar environments, the black holes might have substantial eccentricity, elongating their orbits into ellipses rather than circles. Gravitational wave emission tends to circularize orbits over time, but if the initial eccentricity is large enough, some residual eccentricity might persist down to frequencies where ground-based detectors become sensitive. Detecting eccentric black hole mergers would provide strong evidence for dynamical formation in globular clusters or galactic nuclei, helping to determine the relative contributions of different formation channels to the merger rate hierarchical mergers, where the product of one black hole merger subsequently merges with another black hole, represent an interesting possibility that might explain some of the more massive black holes detected by gravitational wave observatories. In dense stellar environments where black holes frequently encounter each other, a merger remnant might remain in the cluster and participate in additional mergers rather than being ejected by the gravitational wave recoil kick. Over time, this process could build up black holes with masses exceeding what single stellar evolution can produce, potentially explaining detections in the pair instability mass gap, or the generally higher masses seen in gravitational wave detections compared to electromagnetic observations. Signatures of hierarchical mergers might appear in the spin distribution of merging black holes, since merger remnants are expected to have moderate spins regardless of the progenitor spins, potentially creating a population of mergers involving black holes with distinctively intermediate spin values. The gravitational wave recoil kick deserves more attention as it plays a crucial role in black hole evolution and can have dramatic consequences. When two black holes merge asymmetrically, whether due to unequal masses or misaligned spins, the emission of gravitational waves carries net linear momentum in a preferred direction, causing the merged black hole to recoil in the opposite direction, like a rocket. The magnitude of this kick velocity depends on the mass ratio and spin configurations, with typical kicks of a few hundred kilometers per second, but with some configurations producing kicks exceeding 1,000 kilometers per second. These velocities exceed the escape velocities of globular clusters and dwarf galaxies, meaning that merger recoils can eject black holes from their host systems entirely, sending them wandering through intergalactic space. Even in massive galaxies where escape velocities are higher, large kicks can displace black holes from galactic centers, potentially affecting the subsequent evolution of both the black hole and its host galaxy. Intermediate mass. Black holes ejected from their host systems through merger recoils or dynamical interactions in dense stellar environments might wander through galaxies and intergalactic space, occasionally revealing themselves through chance encounters with gas clouds or stars. These wandering black holes are predicted to exist by simulations of black hole dynamics in stellar clusters and merger recoils, but confirming their presence observationally remains challenging, since they lack the steady fuel supply that powers persistent X-ray emission from black holes in galactic centers. Transient events like tidal disruptions of stars or the accretion of isolated gas clouds might briefly illuminate wandering black holes, producing flares that appear offset from any obvious galactic nucleus. Several candidate observations of such offset events have been reported, though confirming that they truly represent wandering black holes rather than black holes in the nuclei of faint satellite galaxies or other phenomena requires careful analysis. The cosmic evolution of black holes through time traces the history of structure formation and stellar evolution across billions of years. The earliest black holes formed when the first generation of stars ended their lives mere hundreds of millions of years after the Big Bang, creating a population of stellar mass black holes in the early universe. Some of these early black holes may have served as seeds for supermassive black holes, growing through continuous accretion and mergers to reach millions or billions of solar masses. The merger rate between black holes has changed substantially over cosmic history, with the rate depending on the evolving properties of galaxies, the density of stellar clusters, and the formation rate of massive stars. Observations of quasars reveal that supermassive black hole accretion activity peaked roughly 10 billion years ago, when the universe was about a quarter of its current age, coinciding with the peak of cosmic star formation, then declined as galaxies exhausted their central gas supplies and formed fewer massive stars. The local population of black holes in our cosmic neighborhood provides the nearest examples where we can study these objects in greatest detail, though the relative proximity doesn't make observations easy, given black holes' intrinsic darkness. Within our Milky Way galaxy, astronomers estimate that roughly 100 million stellar mass black holes populate the galactic disk and bulge, the end products of generations of massive stars that have lived and died over the galaxy's 10 billion year history. The vast majority of these black holes remain isolated or in widely separated binaries where they produce no observable signature, dark and silent reminders of violent stellar deaths. Only a few dozen have been identified with confidence through their effects on companion stars in close binary systems, or through gravitational wave detections of mergers, representing a tiny fraction of the total population. The distribution of black holes within galaxies reflects their formation from massive stars, concentrating toward galactic centers where stellar densities are highest and star formation has been most active. In the Milky Way's central parsec, the region within a light-year of Sagittarius A, observations have revealed a cluster of massive stars in eccentric orbits around the supermassive black hole, and theoretical models predict substantial populations of stellar mass black holes should also inhabit this region, potentially numbering in the thousands. These black holes, sinking toward the galactic center through dynamical friction over millions of years, form a dark cusp around the supermassive black hole, occasionally producing observable signatures when one captures a companion star or interacts with the accretion flow around Sagittarius. A itself. Globular clusters, ancient stellar systems containing hundreds of thousands to millions of stars in regions only a few light years across, provide another environment where black hole populations might concentrate. Early theoretical work suggested that black holes would be efficiently ejected from globular clusters through dynamical interactions, leaving clusters relatively free of stellar remnants. However, more recent observations and simulations paint a different picture, with evidence growing that many globular clusters retain populations of black holes numbering in the dozens to hundreds. These black holes can form dynamically assembled binaries through three-body encounters in the dense cluster cores, with some fraction of these binaries becoming tight enough to merge within the current age of the universe, contributing to the merger rate detected by gravitational wave observatories. The retention of black holes in clusters depends sensitively on the cluster's total mass, central density, and relaxation time, with more massive and less concentrated clusters better able to retain their black hole populations. Observations of globular clusters, using various techniques, have begun to reveal their black hole populations indirectly through dynamical effects on the observable stars and through occasional electromagnetic transients. Radio and X-ray observations of some clusters show point sources consistent with accreting stellar mass black holes in binary systems with cluster stars, while careful measurements of stellar motions in cluster centers reveal velocity dispersions higher than expected from visible matter alone, hinting at additional dark mass from populations of stellar remnants, including black holes. The picture remains incomplete, with uncertainties about how many black holes typical clusters contain and whether any harbor intermediate mass black holes in their centers, but the combination of improved observations and simulations is steadily filling in our understanding of black holes in these dense stellar environments. Moving beyond our galaxy, observations of black holes in nearby galaxies provide comparison points that help us understand how local systems fit into the broader cosmic population. The handful of nearby galaxies close enough for detailed observations reveal diverse black hole populations and accretion behaviors. Some nearby galactic centers host actively accreting black holes producing jets and significant radiation, while others, including our own Milky Way, show only weak accretion at levels far below their potential given the available gas supplies. This diversity reflects varying merger histories, gas supplies, and perhaps other factors we don't yet fully understand that regulate when and how vigorously black holes accrete. The nearest quasar, located in the galaxy, Centaurus, a roughly 12 million light-years away, dramatically illustrates how powerful an actively accreting supermassive black hole can become. Radio observations reveal enormous jets extending millions of light-years into space, powered by a 55 million solar mass black hole accreting gas at the galaxy's center. Despite this relatively close distance by extragalactic standards, Centaurus A appears far less luminous than the most powerful quasars discovered at high redshifts, which outshine it by factors of thousands or more, reflecting both their greater intrinsic power and the fact that we observed those distant quasars during an earlier cosmic epoch when black hole feeding was generally more vigorous. The Messier galaxy, catalogued as M87, hosts the first black hole ever directly imaged, a supermassive giant containing 6.5 billion solar masses. This black hole powers one of the most spectacular jets in the nearby universe, extending some 5,000 light-years from the nucleus and producing bright emission across the electromagnetic spectrum. The Event Horizon Telescope image of M87's black hole revealed the shadow surrounded by emission from the accretion flow, with brightness asymmetry around the ring, indicating that material in the disk was moving at relativistic speeds. Detailed analysis of the image constrained the black hole's mass and provided evidence that it rotates rapidly, consistent with decades of earlier measurements using stellar dynamics and jet modeling. Tidal disruption events continue to illuminate black hole populations in galaxies where the central black hole is otherwise quiescent, with surveys discovering new events at a rate of several per year, as wide-field time domain astronomy expands. Each new event provides an opportunity to study a different black hole's environment and properties, with the diversity of observed events revealing that tidal disruptions can produce dramatically different observational signatures depending on factors like the disrupted star's type, the black hole's mass and spin, and the geometric orientation relative to our viewing angle. Some events produce extremely bright optical and ultraviolet emission as shocked stellar debris circularizes and forms an accretion disk, while others show primarily X-ray emission from gas heated to tens of millions of degrees. A subset of events shows delayed radio emission appearing months or years after the optical peak, attributed to delayed jet launching once the accretion disk becomes sufficiently organized. One particularly unusual class of tidal disruption events shows strong, highly ionized emission lines that persist for years after the initial disruption, remaining bright long after the continuum emission has faded. These events suggest that the tidal disruption launches long-lived outflows or creates structures that continue to be illuminated by radiation from the accretion flow, though the detailed physics remains debated. The existence of such diverse tidal disruption behaviors highlights how much we still have to learn about these events and the accretion physics they probe, with each new detection potentially revealing unexpected phenomena arising in these extreme environments. Returning to the fundamental physics of black holes, the quantum properties of horizons and the information they contain has led to fascinating developments in theoretical physics over the past decade. The discovery that black hole entropy could be precisely calculated by counting quantum states in string theory representations of certain black holes provided compelling evidence that string theory correctly describes quantum gravity, at least for those specific cases. More recently, progress on the information paradox has come from reconsidering what happens to information in Hawking radiation through the lens of quantum error correction, and the idea that spacetime geometry itself might emerge from patterns of quantum entanglement between degrees of freedom in the underlying quantum description of gravity. These developments have led to increasingly sophisticated understandings of how quantum information behaves in the presence of black holes, and how the apparent contradiction between information preservation and Hawking radiation gets resolved. The key insight involves recognizing that after a black hole has radiated away roughly half of its initial entropy in Hawking radiation, subtle quantum correlations between the radiation emitted early and late in the evaporation process allow information about the black hole's initial state to begin escaping. This transition point, where the character of Hawking radiation changes from appearing thermal to carrying information about the black hole's contents, corresponds mathematically to what physicists call the page time after Don Page, who first analyzed when information should begin escaping if unitarity is preserved. The physical mechanisms underlying this information recovery involve quantum phenomena without classical analogues, making them exceptionally difficult to describe. Intuitively, wormholes in spacetime appear to play a role. Not physical traversable wormholes, but rather quantum mechanical connections between different parts of the Hawking radiation that allow information to be encoded non-locally across separate photons emitted at different times. These quantum wormholes arise naturally in calculations using modern techniques from quantum information theory applied to gravitational physics, suggesting deep connections between quantum entanglement, spacetime geometry, and the flow of information near black holes. The firewall paradox represents another puzzle about black hole horizons that has generated intense debate among physicists. The The paradox arises from combining several well-established principles. Quantum mechanics requires information preservation. Einstein equivalence principle says that freely falling observers experience no drama when crossing horizons, and quantum field theory limits how much entanglement can be shared between different systems. When you try to satisfy all these requirements simultaneously for an old black hole that has radiated away significant entropy, you encounter an apparent contradiction. The resolution might involve modifications to the equivalence principle near old black hole horizons, with freely falling observers encountering a firewall of high-energy particles right at the horizon. Or it might require subtle modifications to how we think about entanglement in quantum gravity, or perhaps some other resolution we haven't yet identified. The debate continues with passionate advocates for different positions, reflecting genuine uncertainty about the correct resolution and the need for better understanding of quantum gravity. These esoteric questions about quantum gravity and black hole information might seem far removed from observational astronomy, but they illustrate how black holes serve as theoretical laboratories, pushing our understanding of fundamental physics into new territories. The fact that classical general relativity prediction of event horizons and singularities leads inevitably to quantum mechanical paradoxes suggests that black holes are trying to teach us something deep about how gravity and quantum mechanics fit together. Lessons we need to learn to achieve a complete theory of quantum gravity. Every advance in understanding these theoretical puzzles brings us closer to that goal, while simultaneously every new observation of actual black holes in the cosmos provides additional constraints and inspiration for theoretical developments. In conclusion, black holes represent far more than simple cosmic vacuum cleaners or gravitational prisons from which nothing escapes. They are dynamic, complex objects that come in a remarkable variety of types, spanning more than 20 orders of magnitude in mass, from hypothetical microscopic primordial black holes lighter than a grain of sand, to ultramassive giants heavier than tens of billions of suns. Each type forms through different mechanisms, exhibits distinct observational signatures, and plays different roles in cosmic evolution. Stellar mass black holes form from the deaths of massive stars and populate galaxies by the hundreds of millions, occasionally revealing themselves through X-ray emission when they strip gas from companion stars. Intermediate mass black holes occupy an uncertain middle ground, possibly forming through exotic channels and perhaps serving as seeds for supermassive growth, though their very existence remains debated. Supermassive and ultramassive, black holes dominate the centers of galaxies, co-evolving with their hosts through feedback processes that regulate star formation and shaping galactic properties. Primordial black holes might have formed in the earliest moments after the Big Bang, potentially contributing to dark matter and seeding later structure formation. Rotating, charged, and quantum mechanical considerations add further richness to the black hole phenomenon, connecting these objects to the deepest questions in theoretical physics. From the event, horizon telescope images revealing black hole shadows, to gravitational wave detections of merging binaries, to the theoretical puzzles of information and quantum gravity, black holes continue to fascinate and inspire, serving as cosmic laboratories where gravity, quantum mechanics, and spacetime itself are pushed to their limits, forever challenging our understanding of the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.